we'll record this for Tyler because she's out, and she'll see that there's other information that you guys wrote down on the previous pages too that we'll have that you can use. Number 1 says an initially neutral electroscope is touched with an insulator and has an excess positive charge. Draw on the leaves and show what happens to them, indicating the charge distribution with plus-minus notation. So we're going to take this object that has an excess positive charge, then we're going to bring it close to an electroscope that's hanging neutral. Just like if we take Sparky, how am I charging up the foam? By chemistry. The electronegativity difference between Sparky and the foam. And now, I'm compelled to turn that. So if I got a couple, here's a pop can electroscope. What happens to the leaves? They move away from each other. These are just little pieces of foil. Same happens here. I don't even touch it, do I? If I do touch it, do the electrons transfer? No, it will go back down. It would only stay if what? Yeah, because with a wells, and this is a conductor, so it would get out of the wells and distribute itself. So I had to touch the finger because I had to bring this close. The plate charges by induction, so the electrons shift to the rim, and then I take the electrons. Now this is charged up. If I just take it away without touching it, it's still neutral because nothing ever took them away. Probably. See, if this is positive charge, the negatives would actually go down towards this, which would make this excess positive, which would mean that when I touched it, electrons would flow from me to this. If this is negatively charged, then the positive will go down to it, and the negatives will go around the rim, and I'll take the negatives, and the electrons will transfer from this to me, and now this would have an excess positive charge because the electron transferred out. We don't really know the sign. I mean, there's ways to figure that out, but we didn't figure that out. So we don't know whether it's plus or minus. So I get close to that, right? And now when I bring this in place, what do the leaves do? They go back down because this has that opposite charge, doesn't it? But if I get rid of this charge, now they're going to move out again. Fun with charge. Parlor tricks, right? This is what they used to do before they had TV. To who could figure out the device to build up the most charge and shock their friends more. Okay? Because if you could bring something over that gets Paul's hair to light up, that's pretty cool in the 17th century. Right? Okay. So as we bring this over, well, I'll have to redraw it since I made the leaves like that. But we bring this over, we see that it opens up, right? What's going to shift up towards the positive object? The negative. Which means that these will be positive and they'll move apart. And then when we take it away, because it was an insulator, not a conductor, it would go back to its original because it's only being charged by induction when I go like that. That's induction. There's no conduction unless you have a conductor. You need the metal conductor for the electrons to actually transfer. Okay? So that's one. And number two, we have find the total force on the middle charge. 2 microcoulombs separated by 4 meters to a 3 microcoulomb charge, and separated by another 4 meters to a minus 3 microcoulomb charge. What are the positive and negatives going to help us do in this problem where it says, what's the total force on the middle charge? That's right. So for this one, what do we notice about the charges? The positive, positive, right? So they're the same, which means that it will be attractive or repulsive. Aiden? Repulsive. So that would mean it would move this one that way, or apply a force that way, and apply a force like that. So the force on the middle charge from this green one is that direction. In the case of the blue and the red, we see that the force is attractive or repulsive. Attractive, and that one will be like this. So that means we got to find the green force and find the blue force and do what? Add them, and our total force will be in which direction? To the right, right? All right, so green. Let's step, y'all. Okay. Come on, who doesn't get excited when they hear that at a wedding? Everybody can handle that dance, right? You know, to the right, to the right. What's it called? Yeah. The cha-cha slide, that's right. Let's see, y'all. Okay. Something like that. 9 times 10 to the 9. Well, you can mix them up. Or the Macarena, right? The last wedding I went to, we did a flash dance, too. Did I tell you this story already? Flash mob to Footloose. Oh, the whole family was in it, except for the other side. They had to watch us. We see the flash mob for... yeah, they were, yeah. Kind of an odd. What? Oh, I was in the back. I wasn't allowed near the front. So 0.003375 newtons. Now, when we do the one between the blue and the red, you can see when you plug that in, it's going to be the same values. 9 times 10 to the 9, 3 times 10 to the minus 6, and 2 times 10 to the minus 6. Remember the negatives, they came out just to help us get the direction of it. Divided again by 4 meters squared, so we'll get the same value. But we could see, and now we know because the total force is going to be crust. That's okay. The green plus the blue, right? In that direction. So 0.00375 newtons plus 0.00375 newtons equals 0.00 1.675 newtons. That's number 2. Number 3. Everybody got that written down? Oh, maybe. Oh, I didn't write it down. I didn't write it down right. It's supposed to be 3.3. It's supposed to be 3.3. See, I didn't write this down correctly down here. Sorry. So, and then I just wrote down what was written in my notes. So, whoopsie doodles. Okay, number 3. What's the strength of the electric field? 40 centimeters from an isolated proton. Well, this is easier than the one that you guys just did on the other questions. E K times Q over R squared, right? We have it's a proton, so it's 9 times 10 to the 9 newtons times meters squared per coulomb squared. This electric field is easy unless you make it hard by not writing the equations down on your reference sheets. Then it becomes thousands of times more difficult. Next year I'll make the 5th graders memorize these formulas. No, I'm teaching straight physics to them. Same course. Just kidding. 1.6 times 10 to the minus 19 coulombs is the charge on a proton. Of course, I'm just kidding, right? 40 centimeters, don't forget to make it 0.4 so that your units are consistent. 1 second. Nine times 10 to the minus 9. Oh, isn't that clever? Newtons per coulomb. Yes. Yes. Sure. Yeah. Yes, definitely. And of course, I mean, right? Look. But that's good work, right? The other thing, I mean, she brings up she was working with voltage and potential energy. Of course, what happens if the charge, if it has potential energy, we do work, what happens if we let it start to move back to its original location? That potential energy starts changing to what? Kinetic energy. So let's do one like that. Number 4. So in this one, we have 2 plates. Like so, and an electron. And it's at rest on the left plate when a switch is closed, creating a voltage of 500 volts. Between the plates. Okay, so it's just sitting there, but then when we hook up the voltage and we close the system, connect the wires, uh, flip the switch, this is going to transfer over and move to this plate, like so. And it says, what will the electron speed be when it gets to the other plate? Right? And it's like what you see when you see the spark, the ionization trail from electrons moving into your fingertips. Does anyone notice, like at night maybe, if you sleep where it's very dry and you have a blanket on, and you rub up against the blanket, and then you start to take the blanket off, or you can see yourself sparkle, right? Those are little ionization trails. And it's from the electrons moving. Yeah, well, you could put some water in your room. That would make it more humid. You could use a humidifier or just get plants or just put bowls of water too, or unless you have a dog, then they'll drink the water. And they'll just... So, anyways, we know that we could come up with how much potential energy there is. Because it's an electron, we know Q is 1.6 times 10 to the minus 19 coulombs. It's negative, but we won't really worry about the negative in the sign. It will just, it's by convention anyway. So what is the potential energy of this? Well, it's equivalent to the work, right? And what was our formula for that? E times charge, but we don't have E, but we could also use the formula you have is voltage is U over Q. So UE is V times Q. Joules per coulomb times coulombs, because volts are joules per coulomb, times coulombs gives you joules. So it's simply 500 volts, which is a joule per coulomb, times 1.6 times 10 to the minus 19 coulombs, 500 well, that's not many joules. 8 times 10 to the minus 17 joules. So how fast do you think that's going to get an electron going? Well, what we'll do here, that potential energy, our energy, the sum of the energies initially equal the sum of the energies finally. Remember that when we did conservation of energy problems? Yeah. Well, a voltage is the potential energy divided by the charge, right? So you can, so UE is V times Q. So all I did was take V and multiply it by Q to find the potential energy. Why? A volt is a joule coulomb. So coulomb times coulomb leaves joules. Or joules over coulombs times coulomb leaves joules. Does that make sense? Not really? You don't seem satisfied. What's our initial energies, potential energy, what's that going to become? Kinetic energy, which is 1/2 mv squared. But we don't know what m is, except what is this thing that's moving? It's an electron. So do we have the m of an electron? It's on the reference table. What did you say it was? Pretty light, right? Of course, it's only an electron, so I guess you would expect it to be light. 8e to the minus 17 times 2 divided by 9.1e to the minus 31. 1.758. You should make sure you can do this along with me so you have the calculator work down. Is v squared. So make sure you can get to that point on your calculator. Simple calculations, but there's places you can make mistakes on your calculator. Okay, so then what do? Square root it. 3, 6, 7. So V is 1.326 times 10 to the 7 meters per second. Okay, of course 500 volts, that's a lot of voltage. Car battery's 12 volts. A car battery's 12 volts. A car battery is 12 volts. What? That's the speed. No, it is. It is, but I just said the 500 volts, right? That gave it the energy, the potential energy for that charge, which converted into kinetic energy, which gives us a speed of 1.3 times 10 to the 7 meters per second. I don't know. Maybe you can get different versions. Of course, you got to get the current. It's going to matter too. You can have all the voltage in the world. If you don't have any current, it's not going to do anything. We had to switch flip the switch on it as well. Let's look at let's see. My nose is so stuffed up. Part 8, page 12. Okay, we have a hollow metal sphere with a radius of 20 centimeters. Okay? Is that right? Is that? Well, that didn't last very long. We'll work on that one tomorrow. So really, we're almost done, right? We are. All we got is 2 on the practice problems, all of your moderates, 1 on the hard, 2 projects. The reviews you do on your own. Yeah, do those on your own tonight. Take you about 20 minutes, and you'll be all set.